I wasn't saying it is, but I'll just ensure that this thing is. The reason I find it like, why would anyone talk with this like 15 years ago? You want something simple. It is 12 degrees.
No, there you want to do something accurate because you want to use it. The only way to navigate is this.
Just, yeah, that's
You see the moon, you see the stars. It's the only way to navigate.
yeah, that's
You want to be extremely
okay. I mean, like we are like,
Hello everyone, it's a pleasure to have with us Chatterjee, who just apparently thesis at Generalization. He will talk to us about bounds for dependent data using online to batch conversion.
Thank you, Jitin. Also, thanks everyone for attending the talk so late in the day, and also like shooting this Diwali. I don't know, but yeah, thanks for coming. This is a joint work which was accepted to AI-Stats 2025 with folks at IIIT, Manoj Mukherjee and Alhat Sethi. And in this, we'll be basically talking about learning theory, or as was pointed out to me like quite aggressively, computational learning theory. So we'll, at the end of this talk, we'll understand why this distinction is important, like why the adding of the phrase computation in front is important. But without further ado, like let's start. So we'll start with the three fundamental truths of machine learning. So learning is easy if you assume that everything is easy. It's hard if you assume reality. And the problem is that we do not understand what version of reality we actually have to base our theoretical questions on. So in this particular talk, we'll be focusing on a line of literature that originated sometime in the 90s, and it has proved robust to a lot of the modern machine learning paradigms. So hopefully, like our results are pseudo-realistic, to put it. Uh, Before we start talking about our results, we also have to start talking about what is learning. And Vapnik in 95 gave a pretty comprehensive characterization of the problem of learning using these five constructs. So we have an instance set. So you can think of the instance set as being any kind of a labeled instance space in your head. So for example, you have objects and you have labels. Combine this, you get your instance set. You have some unknown distribution on this instance set. You use this particular distribution to generate training samples from your instance set. You have what is known as a hypothesis class. You have a known well-behaved loss function of sorts. So we'll not be assuming very pathological examples in this talk, but our results sort of generalize to a lot of what is known to be classically pathological settings, but we'll not get into those details right now. And finally, the most important object at our disposal is what is known as the learner. So the learner is a probabilistic map. It takes a set of training samples which are sampled according to this unknown distribution, and it outputs an element in the hypothesis space. And this is basically what I've tried to capture in the diagram. And in this entire setting, we would like to model the performance of our learner in some way. And in order to do this, we model the uncertainty in the performance of the learner into main ways. The first is the true risk of the learner, which is basically the expected loss over a sample drawn at random from the instance set. And the other is the empirical risk, which is what your loss, the loss that the learner concedes on the samples that is given to you. And we understand the problem right of the bat as the following, that because the distribution is not known to us, calculating or minimizing the true risk is not possible. And any kind of reasonings we perform about the true risk have to go through this empirical risk quantity. And Valiant, like in his, I think when he won the Turing Award, like he's famously said to have remarked this fact that learning is inference under uncertainty. So the central goal that we have today is the following, that how can a learner, seeing only a finite sample, choose a hypothesis whose performance generalizes to unseen data? Now, in the way I have phrased this problem, you see that we assume that the finite sample is generated i.i.d. For the first half of the talk, I'll keep the discussions limited to i.i.d. so that I can introduce some of the proof techniques that we later use. Then I'll break this assumption and I'll show you where the proof technique breaks down, and we'll introduce measures to fix the proof techniques. That's going to be the general view of the talk. So in order to answer the central problem, Vapnik came up with what is known now commonly as the ERM rule, or the empirical risk minimization rule, which is we simply, the learner assumes with their heads in the sand that the it knows what the unknown distribution is, and if it minimizes over the given samples, eventually if the size is large enough, it will achieve the true risk, and this will hold uniformly over the entire hypothesis space. And the notion of generalization that we have is basically structured to quantify how reliable Vapnik's intuition was. So, in other words, learnability posed in Vapnik's intuition is an existential question, that does there exist a learner that fulfills this property? While generalization is basically an algorithmic question that, okay, can we bound this quantity, this gen of a comma s? Before moving on to generalization, we'll first try to see how learnability is captured, because it trivially gives us the condition for which generalization holds, and we'll arrive at a necessary and sufficient condition for well-behaved objects. So when does ERM hold? If our hypothesis class is what is known as this uniform Glivenko-Cantelli class, then the ERM condition actually holds. So here we say that your generation error uniformly converges to 0 for every distribution over your chosen hypothesis class. And if your hypothesis class is UGC and your learner only has access to finite samples, then you can upper bound your generalization error using some static combinatorial measure of the hypothesis class. One very well-known example is the VC dimension. And we know that if the VC dimension is bounded or if it's constant, then as n increases, it decreases to 0, which means that the generalization error eventually goes to 0. If we go back to Vapnik's formalization of learning, this basically means that UGC guarantees imply learnability and generalization. However, we also note that in order to arrive at this condition, we imposed a lot of these worst case conditions, right? It has to hold for the entire hypothesis class. So we put a supremum up there. Then we said that it has to hold for every distribution. Then we also implicitly assume that the data is i.i.d. Finally, we also say that the VC dimension has to be bounded in some way. Otherwise, this UGC does not imply generalization. So the problem with all of these restrictions is they don't work as expected for modern machine learning paradigms, because modern machine learning paradigms simply throw the book out of the window. So you have lots of GPUs, you basically can learn random noise, which means your VC dimension is extremely large compared to whatever data set that you are getting. So the condition on the second equation does not hold straight away. Then we do not need to optimize over the entire hypothesis space, right? If our hypothesis space is complex enough, we can just look at a structured subset of the hypothesis space. This is what algorithms like stochastic gradient descent do. Finally, the overarching question of the data dependency. Everything over here assumes that our data is i.i.d. or not per i.i.d. per se, but it also allows some martingale structure to it. It is not necessary that our data has to be well behaved under these circumstances. So basically, this UGC plus ERM approach does not work in the modern paradigm. Great. What works in the modern paradigm? So one example of what works in the modern paradigm is what is known as this packed Bayesian approach. So because UGC plus ERM bounds are too pessimistic, McAllister, as early as 99, introduced the notion of inducing distributions over the hypothesis space instead of picking elements from the hypothesis space. Now, you start with a data independent prior and you see what distribution is induced on the hypothesis space. And for any prior and posterior that is induced with high probability over the sample, McAllister showed that such the bounds on the board are possible. So, for example, it need not just be KL divergence. You can go for most information theoretic divergences and they work. So this particular setup is known as a packed Bayesian setup. And here the bound basically depends on how far my induced distribution is from my chosen prior. Now, the prior, you can play around with the priors, and this is what basically implementation or application people do. They choose different priors and see how well the algorithms are performing. But if you theoretically assume that your prior is good enough, this allows us to account for the generalization behaviors of SGD and other algorithms which do not uniformly generalize over the hypothesis set. On the other hand, the generalization gap, because it depends on an information theoretic quantity instead of a combinatorial measure of the hypothesis space, it allows us to account for generalization behavior of models which sort of fit random noise, in fact. It's great. Pack-based is great. But
I mean,
yes.
what your posterior is will depend upon what script edge is.
Yeah, definitely.
Yes, so the generation gap does depend upon the commutator measures. It's just a different kind of dependence.
So, for example, you can also think about this that you do not need to uniformly depend on the entire hypothesis space. So, earlier the VC dimension kind of measures sort of took every hypothesis in the hypothesis class into account, right? So here I can simply say that okay, you focus the entire probability mass on a small subset of the hypothesis space. So even if your hypothesis class actually is the support for your posterior distribution, it does not influence the posterior distribution as much as combinatorial measures.
Yes, I mean, like, see, I
Yeah.
mean, also you could have done something like, okay, so all you're saying is that you have now put a measure. So, like, if something is going wrong in a small measure set, that's not a problem. But that's about it, right?
So
I mean,
Yes,
so
exactly.
that's the difference.
that's it.
Yes, exactly.
Hmm.
So, okay, is pack-based the silver bullet? The problem is that in applied settings, it has been observed that even pack Bayesian bounds are quite loose, actually. The reason for that, the pack Bayesian generalization bounds do not take into account how the algorithm actually evolves over its training. So we also need to take into account some of the algorithmic dynamics that are abstracted away in the pack Bayesian setups. In order to address this, there have been a lot of tools and techniques that have been introduced over the years. One of the most recent techniques that have come up, and this is with an asterisk, if there is time, I'll explain the history of this technique a little bit later. But the most recent technique that was introduced in the i.i.d setting to account for these generalization bounds are the online to pack framework. So the key idea in the online to pack framework is as follows. So you take your offline learning algorithm and you design an online learner that follows the offline algorithm through sequential updates of the data. So if you're familiar with online algorithms choose to minimize their regret with respect to the optimal offline hypothesis. However, in this case, we change the target from the optimal offline hypothesis to the offline hypothesis that we are trying to bound in this case. So I'll become a little bit more formal in the upcoming slides. But the idea is that we build an online process that mirrors the incremental updates of the offline learner. We express the generalization in terms of how the online process tracks the regret. And we translate this regret into the generalization bound. This is the overall idea. And why this matters is it replaces, as Piyush was saying, like it does not substitute, does completely throw combinatorial measures out of the window, but it allows us to replace class complexity by algorithmic complexity. This also allows us to link adversarial bounds with average case analysis. So let's come to the main framework of the online to pack framework that uses an auxiliary online learner. So the offline learning setup is at time t, you take a subset of the data. So you fix an ordering of the data beforehand, and you take a subset of the data, which is taken by i.i.d sampling, and you say that your offline learner produces the hypothesis A over ST. In the online learning setup, the online learner that is supposed to follow this particular hypothesis now has already seen its own hypotheses beforehand, and it already knows what losses it has incurred. So now at this point, it chooses the best possible online hypothesis, and then we finally measure the regret against this particular hypothesis, which we call AT. And the sequence AT basically captures the trajectory of the offline learner on these incremental updates. This is a more formal way of approaching this. And this cumulative regret term, which basically measures the stepwise difference between the losses incurred by your online learner and the loss incurred by your offline learner at the same point in this trajectory, becomes the important quantity that we require to bound our generation equations. So the theorem which Lugosi and you present informal is as follows: that if you have bounded losses, if you have i.i.d data, if you have any online learner with this cumulative regret RT against your comparator sequence AT, we have with high probability that you get this concentration inequality over the generation error, that we have in expectation your generalization is upper bounded by the expected regret plus a term that grows smaller than the number of samples. So, yeah.
One question. So in what sense is the learner supposed to be online? So, I mean, it cannot. So it is supposed. I mean, AT is also producing a hypothesis at each time.
Yes.
So in what sense is L different from AT?
Yeah. So AT basically is when you train that offline learner on the same set of
First three samples,
points.
but the online learner
Yeah.
has seen the first three samples. Right?
Yes, but the offline learner now, so the online learner cannot go back and fix the mistakes it has done with respect to the previous terms, right? But the
Also,
offline learner,
okay.
yeah,
So it's allowed to look at everything, but it can only be evaluated on this latest.
yes. So the high-level proof sketch is as follows: that we show that for bounded losses, the generalization error is upper bounded by the cumulative regret, a concentration inequality term, and a stability term that quantifies, in some sense, how my offline learner trajectory changes as more data is revealed. And we'll also discuss this last line where we say that this is often growing smaller than the number of samples that we have. And once we can prove this intermediate equation, we simply take an expectation over the samples and over the algorithmic randomness to obtain the kind of bounds that are stated above. And I'll go through the proof sketch quickly because the proof sketch is pretty straightforward. So you start with this very cryptic looking quantity which measures the empirical, so the true risk of the offline learner at some point in the training process with respect to the loss incurred at the TF data point. So why this particular random variable is required actually comes about from the analysis. But take my word for it that this is an interesting like random variable to look at. And we see that this particular random variable actually forms a marginal difference sequence. Because it forms a marginal difference sequence, we can now
Is there a t plus 1 versus t there? So AT should be evaluated on ZT plus 1, right?
yeah. There's I think like there's a t plus one. Yeah.
Yeah.
Right. Yeah. So I in fact spotted this just before the thing started. Yeah. Okay, fine. So because this sequence of random variables form a marginal difference sequence, we essentially can bound the sum of these random variables using these Azuma-Hofding-style inequalities. And this concentration inequality, so this particular equation, controls the deviation between the population and sample loss along the trajectory of the offline learner at various time points. Now, what is required is we need to connect this to the cumulative regret bounds at some point. So with some algebra, we'll notice that this particular term can be upper bounded by the loss incurred or so it is lower bounded in fact by the loss incurred by the offline learner on the entire training set. So this gives us this final inequality. So without going into too much of the specifics, what connecting the regret bounds to the martingale inequality gives us is a way to control the deviation between the true risk of the comparator of every offline point and the empirical risk itself. Armed with this knowledge, we now actually look at the quantity that we are supposed to bound, which is the generalization error LD minus LS of AS. Again, I will like ask you to take my word for it. If you are uncomfortable, feel free to go and look at our paper, but you can actually decompose this in the style of these bias variance trade-offs into the following three groups of sums. The first group of sum controls the change in true risk as data accumulates. And we say that, okay, so let us suppose that this particular term is upper bounded by the stability 1A term. So which measures how the comparator shifts with respect to the true risk. The second term is something that we already saw how to bound because we already saw how to bound the term inside the summation in the previous slide. So we can bound this using concentration inequalities and the cumulative regret. The final term controls the change in empirical losses between the comparator and the actual offline algorithm. So let us bound this term also by a overarching stability 2 term, and we define one particular stability term to club these two terms together. So we'll talk about this particular stability of A in the next slide. So collecting all of these together straightforwardly gives us the fact that the generalization error is okay, there will not be a plus here. The generalization error is straightforwardly upper bounded by the regret, the average regret, the concentration inequality, and the stability term. Taking expectations, we arrive at this particular conclusion. And if you recall, the only thing we need to do in order for this expression to match the theorem of Lugosi and New is to account for the fact that this last expectation term vanishes. So now the question is, when is this expected stability term going to disappear? In the offline setting, so there are two ways of looking at when the algorithm is actually stable. The offline view is that adding or removing points from the data set do not really influence the output of the offline learner that much. The online view is from iteration to iteration, your outputs actually do not change that much. So we'll call the first the notion of uniform stable algorithms. So this was introduced in 2002 by Busky and Elisov, while this contractive updates notion was introduced by Lugosi and New themselves, where they now allow us to do a very particular thing. So imagine if you cannot straight away claim that your algorithm is uniformly stable in some way, you can offload the task of stability to the intermediate artificial online learner. So if you can design an online learner that has contractive updates and it tracks your offline learner, then you can once again you can claim that this term vanishes.
This is a little bit strange. So it has to know the horizon. This
Yeah, sorry.
so this stability depends upon how big the horizon is, like the capital T. So at each time, so you're saying that when you
Yeah. So replacement stability basically tells us that if your training set increases in size, then your stability increases. So the more
so
it's
that,
actually
how does that happen? I mean, like the AT is just looking at small t samples, right?
yes,
So how is it? How is
but
it?
AT is the offline learner, right?
On capital T
So
samples.
yeah,
But
offline
I mean,
learner
how
on
does it
capital T.
run to a smaller number?
So I think maybe we can just go back to where AT was defined. I think that made it clear. I think it's a small thing. So yeah. So
Hmm.
the thing is,
No, so A is some learner which at a given
Yeah.
time
So
will produce
yeah,
yeah, so it is defined at each time t, and
yeah,
now yeah, so whatever its sort of
hmm,
stability is can at most depend upon small t.
yeah.
Uh,
So I think you want to. I think this will make it more clear. Yeah, yeah. Now we can discuss this. Yeah,
yes, yeah, so that's fine. So
yeah.
so this contractive updates, that's the thing I'm
So
everything hypothesis will be some vector, right? And
yeah, so the contractive updates is the term that influences this particular point, this L of HT. So
uh,
this equality is what is controlled by the contractive updates. So there is a relation. So the cumulative regret is defined with on the difference between your offline learner and the online learner
that
at
is fine. No,
right.
but it's
So
definition of this contractive.
yeah, I think
yeah,
that's the problem now. So I think the issue is that the LHS doesn't depend on capital T at all.
Yeah, that's that's another thing. Yeah.
uh,
So how is it possible that?
yeah. I think so. The idea is that if let's say you fix some sample size, right? So if you fix the number of samples, then your contractive update basically tells you that this cumulative regret term is upper bounded by a constant. So the sum of cumulative regrets or the cumulative regret term itself is upper bounded by a constant.
I mean, for example, this would be true if it was decaying like quadratically, right? So if it was gamma
Yes,
by small t squared,
it can decay any like it can decay like sublinear decay is fine for this.
yeah. So
Yeah,
n squared or something. But
yeah,
okay. So
yeah,
that's fine.
yeah.
So the
Yeah.
final thing is this, that the sum of the
Yes. So in fact, like I would have come to this point later. So one of the main challenges with the online to pack setup is the following that we are pushing the stability notion onto an artificially constructed online learner, but the bounds themselves might still be vacuous if you actually do not instantiate the bounds using a family of online learners. You whatever bounds you derive, you actually have to also give a family of online learners that conform to those bounds. So for example, we have yet to see an example. So I'll show an example of a class of online learners that actually are stable in this contractive update or a generalization of this contractive update technique.
So for example, if you just run OGT,
Sorry,
online gradient descent,
sorry.
this is not constant, this is square root t. I mean the sum of norm of 80 minus 80 minus. Just run plain
I'm
OGT.
sorry, I can't hear.
Micro thing.
Yeah, maybe. Yeah.
Yeah.
So I need to say that if you let's say I just replace this online learner with the plain OGT. Am I audible now?
Yeah.
Yeah. So then this definition, this condition doesn't hold, right? Because
Yeah. True.
then what kind of are you assuming some sort of stability assumptions on the
Yeah. We have stability. Yeah. I mean, the point. So the learning theory literature, the people have actually shown that you cannot do much without stability. So in the i.i.d case, in fact, stability is a necessity condition for generalization. So you have to deal with the stability in the offline case, or you have to push it to the online case. But
But that's the
unstable
thing
algorithm.
that there it's like not such a strong thing, right? So there it's enough if you're, I mean, like the usual like
Uh,
everything is prosperity
I actually I disagree actually. So if you look at the
but
uniformity
1/t,
stability,
right? 1/t is what you get, right? I mean, like you usually have something like that. If you change one data point, change by a constant, and you're averaging by t. So 1/t. You're asking for
yeah.
1/t square. That's a lot.
No, but here is the thing, like that's the caveat. So imagine that you are telling me that you can replace so if you look at the original Busquets-Elisa paper, they actually use this in a triangle inequality sense. So you
I'm
can
asking for something very basic. So like usually when I
yeah.
write down an estimator as f of x1 to xn. Like the
Yes.
typical situation is that if I change one of them, it changes by, let's say, the best thing is it changes by a constant. Like that's a kind
Uh,
of Gaussian type thing. Right?
yeah.
You have that, and then you're averaging, then you will get one by t,
Yes.
right? One by small t,
Yes.
not one by capital T, but one by small t at time t. And
Hmm.
then it will of course be diverging.
Yes.
The example which I was giving was diverging even faster. So
Yeah.
this has to be some special, like this has to be like not just some generic thing, right? It has to be somewhat.
Yeah. So it's specifically it is replace one stability. It has to conform to this
Okay.
replace one stability condition. So
Maybe we'll
uh,
see some examples of some estimators which satisfy it.
yeah. So at the end of the talk, so I'll introduce the various notions of stability, and like maybe we can have a discussion then.
Okay. Okay.
Yeah. So the point. So okay. So the point is that it's great that we stopped here. Is we understand that this small block actually makes or breaks the generation bound in some way. So if if there are no stability notions that guide our learners, you actually cannot get generation bound. So in in a sense, this is fairly natural because if you think about it, if your algorithm behaves very unpredictably, then there is no guarantee that it will even learn under Vapnik's formalism. So this is basically a way to theoretically characterize this predictability in learning systems. So with that, we move on. So by if the stability condition holds, then we arrive back at the earlier bound that we saw. Great. But as you can see that we still have 10 slides left. So what is left over here? So the problem with this is that the algorithm, the framework crucially uses the fact that our data is sampled i.i.d. Even if we do not have the fact that the data is sampled i.i.d., we need the losses of the online learner to form a martingale difference sequence. This is quite a strong assumption that we place. So the question is that because we know that stability is sufficient for generalization, in fact, it's necessary, which was proved very recently. Uh, uh, we would also like to ask ourselves the question that what about non-i.i.d settings? Like, can we say that stability is sufficient for non-i.i.d settings? In order to ask this particular question, we also have to ask ourselves the question that exactly what kind of non-i.i.d-ness are we looking at?
Hi, Sagnik. I'm sorry to.
Yes. Yeah.
Could we see the example? Because I am very troubled by this. So,
Yeah.
I think it's a question of indexing. It's or
Yeah.
not. So it's,
yeah.
So these are the different notions of stability. Oh, so are you talking about the online learner that has the stability guarantee?
the uniform stability, that's the kind of thing I would have thought is what is called stability. You change
Yeah,
one
yeah, yeah,
component
yeah,
and you change by a
yeah,
constant.
yeah.
Yeah, so I think we should asking the simple question, which is About a question of dimensional analysis, right? Like just think of it that way. That that for typical algorithm, you expect that the 80 minus 1 would look like 1 over 2.
Yeah.
And therefore,
Yeah.
Like you only need the sum. You only need the
Minimum
sum,
sum, yeah.
not
So,
sum over c.
so somehow for some you get away with it. And even though
The sum is weaker increment, right?
yeah, it's bigger. And so I guess the question is that is there a good example where is it like a nice example where I can show in some way that this is constant?
So, off the top of my head, I cannot recall a nice example for which this works, because these are like fairly the proof techniques are fairly like
Yeah,
abstract,
we
but
take the first one, this BE02.
yeah.
So that is the simplest one. So you change one of the examples and your loss changes by a constant at most of it.
Yeah. So
And
it's not just change, by the way, Piyush. It's also you can include an extra example and you can exclude an example as well. So
yeah.
yeah.
Change one.
Yeah. Yeah.
Replace, yes.
Yeah.
So in this one, I mean, this is not exactly your AI and AI minus one in some sense, right? Because if you did this
No.
here,
Yeah. No.
there's some
Yeah.
kind of normalization that is going on.
Yes.
Okay, so maybe you see in the
Okay,
proof
okay.
there.
So like, can you tell me what is the exact problem that you're having? Because yeah.
So for example, like if I were to imagine that this L of ASZ is AI and L of ASIZ is AI minus one, then
Okay.
clearly this is not fitting into the contractive setup, right? Because this is
No, but see, again, the problem is this: it does not have to fit into the contractive setup. So the contractive setup is purely for online algorithms, and the contractive setup comes into play when we are talking about online to pack conversions. All of these notions of stability do not assume the online to pack framework to begin with. They have different generation
but
frameworks.
that expression that AI was not for the online learner, that was for the original learner you want to analyze.
Yeah. So the contractive update condition is a much stronger condition than this, by the way.
Yes,
This is a much
Yeah.
So this is a much weaker condition, in fact.
Yeah.
okay.
Yeah. So
That AI there was not actually the original learner you started with, that was some other thing in.
yeah. Yeah. Like, is that like fine now?
At least yes.
for now.
Yeah. Okay. Yeah. So we were at this point that we saw the one crucial point where the proof technique that we saw earlier breaks down. That if we do not assume the losses to be a martingale difference sequence, or if we do not assume the data to be an i.i.d. Sample data, then our earlier proof does not go through. So let's investigate a particular representative of a non-i.i.d. setting, and the most like used non-i.i.d. setting are these mixing stochastic processes. So if everybody is familiar with mixing processes, I'll go on to the but okay. So a mixing stochastic process is basically a stochastic process where you have a structural property that describes this degree of dependence between blocks of random variables along the stochastic process. So you can essentially use the mixing property to control how dependent your data is at certain time points. So we will be using this fact crucially in our proof technique. So before we go into this particular notion of non-idleness, we'll see a particular example of a mixing stochastic process. One might also ask the question at this point that, okay, why are we even going for such a well-behaved non-ID setting? Why can we like, is the degree bounded? Does the degree grow with the size of the block that we are looking at? You can also look at much stronger notions of dependence where between blocks of random variables, you can barely understand how the dependence is characterized. So the question, just to preempt all of those questions, I'll just say this, that possibly we can do something under stronger notions of idleness. It's just that the mathematical tools are not available to us yet. So people have looked at this. Mixing processes have come out to be a model where federated learning setups are actually deployed. And people also have looked at generalizations of the stochastic process that we'll be looking at. And people have found that those like mathematical tools for bounding the losses do not really work. So just with this disclaimer, we'll move on. So this is an informal view of a mixing stochastic process, like just like for visualization. And the typical mixing stochastic process that we are considering are these weak Bernoulli mixing processes or beta mixing processes, where if you have two blocks of random variables that are infinitely separated, then their joint distribution is equal to the product of their marginals. But it is only true when the blocks are very far apart from each other. If the blocks are closer to each other, then this independence quantity breaks down. So in some sense, they're asymptotically independent, but in the finite sample regime, they are not independent. Uh, we also, so the R paper uses this, so we'll not be discussing about this. R paper actually uses a weaker notion of beta mixing. So weaker from the point of view of using the mathematical tools. We do not have so many tools available to us where we consider this independence to hold only for a single slice marginal in the future. We do not even assume an independence over the entire block. So, but this is not crucial to the proof sketch today. So we consider the case where our mixing stochastic process is converges to a stationary distribution in expectation with respect to the total variation distance, and we call this the beta mixing coefficient. We define the beta mixing coefficient this way. Ignore the phi mixing, we do not require it. It's just if we remove the convergence in expectation, if we simply demand a stronger notion of convergence in total variation, then it becomes a phi mixing process. But for now, the beta mixing process is a process where this beta k coefficient goes down to 0 as the blocks go far apart. So this is what our beta mixing stochastic process is. So exactly what I informally described in the last slide is captured by this mathematically. Now, the online tool, as we have already established, that we need something to account for data that is drawn from these beta mixing processes. So the setup is as follows, that at each round, the learner now outputs a posterior distribution over the hypothesis space. So we are in the paired Bayesian setup to begin with. And once the TH sample is released to us, the learner incurs an expected cost. Under dependence, the sequence of costs are not martingale because they do not telescope cleanly. So the resolution is as follows. We follow this blocking technique by Yu from 1984, where we basically break this dependent sequence into two parts. We break it into a martingale part and a remainder part. And this martingale part can now be controlled using these Azuma-Hobding bounds that we saw in the first part. The only thing we need to deal with are these remainder terms, which sort of collect this dependency drift between different blocks. In order to control this particular remainder term, we have, in this work, we introduce a new notion of stability. So this notion of stability limits how much our posteriors drift between rounds. At this point in time, after our paper came out, there were two follow-up works which actually uh, also show how to do the same process without introducing new notions of stability. So the idea in those new works are as follows. We in the online learning game, we give a little bit of power to the online learner and allow them to see some T steps into the future. If you do this, then the remainder term can be controlled by the power that you give to the online learner. That is the delay that you introduce in the online learning process. So you convert the setup from not from an offline learner to a purely online learner, but from an offline learner to a batch online learner. and your remainder term is now bounded by the size of the batch that you are going for. Uh, while that particular technique has its own uses, um, I personally prefer working with this new notion of stability because this also has connections to other mathematical objects that we have like present in the literature that we will also go towards. So the notion of stability that we introduce for the purposes of controlling the drift between these posteriors in the dependent data setting is based on Wasserstein distances of order 1. So if you have two probability distributions, is basically the optimal transport cost to transform one of the probability distributions into the other. It's like you have a bunch of sand, you have a hole. What is the cost needed to put the sand into the hole? So this is a fairly natural notion of stability that has been seen before in these Washington GAN ideas of papers. And the interpretation is that if my learner has a small drift between rounds, this means that the posteriors that I'm outputting are close in optimal transport, which means that this is another way of saying that my learner does not behave very unpredictably. So, given this, if you assume Lipschitz losses, so you do not need to assume uh, bounded range losses, which is what Lugosi and you have ordered. So you can actually go for Lipschitz losses. It's easy to see that you can again control this drift between posteriors using this Wasserstein stability term and the Lipschitz constant on the loss. By telescoping, you again arrive at this cumulative regret term in terms of this summation of Wasserstein stability terms and the Lipschitz loss. Again, the same question might arise: what happens if these terms do not go down like quadratically, let's say with respect to t, or what happens if these terms go up? The simple answer is then the generalization argument does not go through. So it only works if if the KT terms themselves are sublinear in nature. Fortunately, there exists online learners which actually conform to these. But coming back to the topic at hand, we see that using this cumulative Wasserstein drift, we can control the total non-martingale bias. Now, combining the Azuma-Hofding bounds on the martingale part and the cumulative Wasserstein drift on the non-martingale part, we arrive at our generalization bounds in terms of the regret and concentration inequalities, and two extra terms that one of the terms depends on the decay of the mixing process itself, and the other term depends on this Wasserstein drift. In the i.i.d. setting, both of these terms go to 0. So essentially, our generation bounds are optimal in the i.i.d. setting, as has been shown. In the non-i.i.d. setting, as we'll discuss further, it's still an open question. Um, Again, taking expectations, we get the expectation version. So essentially, we arrive at these concentration inequality bounds. This is very cleanly summed up in this particular theorem that we have. And returning to a point of discussion that we had earlier in the talk, we still need to prove that online learners which fulfill this particular notion of stability exist. Fortunately, the multiplicative weight updates method actually fulfills the Wasserstein stability condition. So the argument actually goes to the fact that if you look at the Donsker-Vernon variational form of this multiplicative weight or the EWA form, you can bound the updates in terms of total variation. Now, the Wasserstein distance parameters can also be bounded in terms of total variation. You apply Jensen's on either side, and you can show it's not that straightforward. It's quite so the algebra is quite dense, but the idea is just simply the fact that you look at the variational forms of these learners. And this is a great thing for us because we do not need to spend more brain power on designing the online learning part. It's just a plug and play. Now that we know that online learners fulfill this notion of stability, you can simply take an arbitrary offline learner, you take an EW algorithm and send it tracking the trajectory of the offline learner. If the online learner terms or if the Wasserstein drift is bounded, then your algorithm generalizes, otherwise it does not. That's the idea. The other good part is because the Wasserstein stability condition is actually a much more stricter condition compared to the uniform stability condition, because now we do not require explicit changes in uh, the data set itself. It's also an interesting question to ask whether this generalized uniform stability conditions and this particular stability notion of a condition, they are related in some way. So the relation between these stability conditions is not actually clear a priori, which also leaves open a lot of interesting work in this direction, because one would like to characterize all the notions, or like the exact stability notion that is needed to sort of capture generalization in the non-i.i.d setting. This is a major open question. So again, coming back to a recap of stability norms. So the exact stability norm that I am talking about is this Mohri and Rostamzadeh's generalized uniform stability. So this is actually yet to be investigated whether this particular norm has anything to do with the Wasserstein stability norm that we have introduced. We have actually observed that this DP stability is captured by our Wasserstein stability notion. And so it's not apparent from this particular formalization, but if you are aware with the literature of DP, then differential privacy norms come up across from these Salis max divergence information theoretic bounds. Now these Salis max divergence bounds are weaker than your optimal transport. So in some sense, our Wasserstein stability actually generalizes DP stability. Another interesting,
Sorry, I don't understand.
yeah,
Because see, so the DP
hmm,
criterion is, I mean, I don't know
yeah,
what is weaker and what's stronger. So like in the sense
yeah,
that if you have the DP condition, you also have total variation, and you have
yes,
almost anything you want, right? I mean, any of the things. I mean, any integral you can do with this, and they will
yeah,
with the epsilon.
yeah.
So are you saying?
I'm talking about the lower bounds.
So you're saying that DP stability will imply Wahlstein stability, right? Is that what
No,
you're saying?
no, Wasserstein stability implies DP stability.
That is, no, total variation does not imply DP, for example.
No, total variation does not imply DP.
But
So
Wasserstein is total variation is one particular special case of Wasserstein.
yeah, yeah, no, no. So the implication does not go via total variation. So the implication
No, but
goes
I'm
via,
saying I can
yeah,
instantiate Wasserstein with the total variation metric,
yeah,
the point metric, it will be total
yeah.
variation. Then what you said should you say that total variation implies DP, but that doesn't happen, right?
No, I did not. Did I say? Then I misspoke if I said.
Yeah, so
No, no, yeah,
I'm
yeah.
trying to figure out. So DP, so when you have DP, you have
So I said that DP is like Salis max divergence implies to DP stability.
no, let's take
Yeah,
this Wasserstein
yeah, yeah,
DP.
yeah,
So
yeah,
if you have this condition, you also have total variation and probably also your Wasserstein unless the distance really badly behaved.
yeah, yeah. That is true.
Because I mean, any integral for one
Yeah,
measure
yeah,
is within a 1 plus minus epsilon of the other.
yeah, 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 yeah.
So that's what you're saying. That this is a stronger requirement than what you were.
Yeah, yeah, yeah.
Okay. Then.
Yeah. But again, so the last 2 points, the last two stability notions that we have listed here, I would personally like to understand how these notions of stability relate to our introduced new notion of stability. And like, if you actually can give a relation between the state of mutual information and Wasserstein stability, I think it has implications elsewhere as well, like not just limited to learning theory. And finally, placing our particular results in context, we see that we give the first set of algorithm specific generalization bounds that work for beta mixing dependent data, which do not require explicit stability conditions on the batch learner. And this again was later generalized by this group, the same group of authors in a series of two papers, where they first simplified the construction in one way, and the second, they generalized the beta mixing dependency to what is known as this graph mixing dependency, where they assume that the data is drawn from this two-dimensional object now. So you have a graph, you have a mixing stochastic process on the graph, and the data is now sampled from this graph. So I actually myself I attended just the talk. I was not very clear on how the graph mixing property works, but yeah, this actually sounds like another interesting way to generalize the notion of non-IIDness, at least in the direction that we looked at. So yeah, our work in one line is that we extended this i.i.d framework to obtain generation bounds, and we this is the things that we have seen so far, that we showed where the classical argument fails. We recall the online to crack framework. We show why introducing dependent breaks the martingale argument. Then we introduce this coupling fix. We derive new bounds, and I did not show you, but EWA actually instantiates these bounds. Future directions, as I've been like saying for this spoiler alert, I've been saying for the entire like talk that lower bounds and necessity of stability assumptions in a non-IID case, while we like because stability assumptions are necessary in the IID case, one would also assume that stability conditions are also necessary in the non-IID case, but it has yet to be proved formally. And the another like nagging question is there like what notion of stability actually characterizes non-IID learning and generalization? So that's a much harder question. And if we move for a second from generalization to learnability, the same questions are still open. So instead of looking at these algorithmic constructs, if we simply ask the question whether the hypothesis class is learnable at all, this is also an open question. And there was a paper, so if you Google learnability in non-IID, there was a paper that I'll not state the name of the paper right now because of the sentence that's going to come out next. We have discovered several flaws in the proofs of that particular paper. So there was a proof paper that was claiming to have proven that stability, in fact, this RO stability characterizes learnability in the non-IID setting. However, the arguments, even though the theorems seem plausible, the proof level arguments actually do not go through. So this is yeah.
Another question. So
Yeah.
So just to understand what you're asking for like a very precise calculation in the sense that for every distribution, if you have
Yes.
what you're saying, the stability implies generalization. What you want to show that if you are generalizing, it should have this that.
Yes. So yeah, I mean all these questions are open basically. In the non-IID setting, the field has just started, so as to speak of.
But that is like so.
Yeah.
You will have to have some model of non-IIDness, right? Like
yeah. So the idea is that you take a so the idea considered by this paper that I am referring to, which shall remain unnamed. So they actually consider that you take these beta mixing processes, a series of beta mixing processes, and you define learnability with respect to this series of beta mixing processes. Like, so there are these ideas that seem very good, but then again, the proofs have to be looked at carefully for these things. So
the series is converging somewhere, or
yeah, yeah, that is the actual problem. So they claim that the series is converging, but then the way they claim that the series is converging sort of nullifies the mixing property at all. So it simply becomes a Markov chain in some sense. So like there is no requirement for this K to decay asymptotically. So there's this like second level convergence that they are claiming happens. So which is and then the I mean, there are straight up problems with the proofs in other places as well. So yeah. So and the final notion is this that this was actually pointed out to us by the authors of this paper that Wasserstein stability is like very similar to this notion of one-step differential stability. And they also listed a lot of these information theoretic notions of stability that like are characterized by Wasserstein stability. Like they are captured by Wasserstein stability. A very nice question that one can answer is that can we use Wasserstein stable online to batch conversion constructions to obtain tighter bounds for differentially private learners? So generalization bounds for learners are stuck in this regret term, right? As we have seen. But if you add additional structure onto the underlying offline learner, you can actually tighten the regret term up. So the question is that can you do it using this Wasserstein stability condition? So one example of where they have actually tightened the regret term up is in this particular paper where they show this one-step differential privacy stability. So this is another question that can we do this? So for example, let's say you assume the same setting, you have the beta mixing setup, but instead of a general offline learner, you have a differentially private offline learner. What are the bounds now? So with this, my talk comes to an end. And like, thank you very much for sitting through and asking questions. Yeah.
Any further questions? Okay, thanks, Agnew.
Yeah.
More handle for the minutes.
Sorry?
English hand back for a few minutes.
Yeah, yeah. So I think like Piyush, you did not get to see this part of the argument during the thesis, right?
Sorry?
You did not get.
I think I
Yeah,
saw, but
yeah.
I probably forgot.
No, I mean
Sorry about
also
that,
no,
yeah.
no, I don't think I covered this like very extensively during the defense.
No, but I read the thesis, right? So
True,
so
true.
I not, I mean, this part I remember reading recently.
Yeah.
But then I forgot the.
Yeah. So the paper that so are we like have we stopped recording?
No.
Yeah, actually, that's kind of what I was going to ask you. Like, it's always
Yeah. So I mean yeah. So so there's this paper like if you're interested, Piyush.
Just wait.
Yeah.